I welcome you for this lecture on NPTEL course on earthquake resistant design of foundations. And as we discussed, this consists of 5 modules, and we was discussing the third module, that is on pile foundations. Within the pile foundations, these are the topics which we have discussed. We already covered piles for static vertical load, then lateral load on piles was also covered along with some numerical examples. Today we are going to discuss dynamic analysis of piles, and in this dynamic analysis of piles we will going to consider both vertical load as well as lateral load. Now the issue comes here, then what is the difference between the second and the third component, that is the lateral load on piles. In the second component, lateral load was considered as a static load only. As you may be aware that we have discussed 2 theories in the second module. One was for the case when we assume that modulus of subgrade reaction is constant with the depth, that is normally for the clay, and for that case we have used Davison and Gill method. And the second one was when the modulus of subgrade reaction is linearly varying with the depth, and that is that is mostly applicable for sands, and for that we have used Rich and Matlock approach. But in both these approaches, the lateral load assumed was not varying with the time, rather we considered a static lateral load here. Today we are going to consider the time varying lateral load, and when we say the time varying lateral load, in that case you may be aware that one of the important issue in the dynamic analysis is called, what is it is called, the natural frequency of the system, and that need to be work out. And once the natural frequency is known, the next step in dynamic analysis is the response of the system. So today we are going to talk about the dynamic analysis of piles, and this has been covered under these subheads. What are the different approaches to carry out the dynamic analysis, which we are going to talk in the first, and that approaches are applicable for both vertical piles as well as lateral loads. And then we are going to talk about piles under vertical vibration, where the load applied is simply the vertical, though this will not represent the real case, but this vertical load may be due to other reasons also. It could be due to machinery or maybe some man-made loads. So load considered is vertical. And the third component is the major component of the today and the next lecture, that is piles under lateral load, which will be covered under soil pile system, natural frequency of the system, and once we carried out the natural frequency, then we are going to talk about the response also. And once response is over, then method of seismic analysis and design of piles, and finally we are going to talk about some numerical example also. So let us talk what are the different approaches for dynamic analysis of pile foundations, and these have been, there could be many way, but normally they are grouped under 3 heads. The first one is the soil is modeled as continuum, which correctly represent geometrical damping as well as inertia of soil. However, in this case it is assumed that soil medium is elastic, therefore nonlinearity of soil cannot be considered in the continuum models. So that is the drawback, but the good point that you can consider the geometrical damping, or what is it is called radiation damping, as well as inertia of soil. Then the second approach, where the soil pile system is represented by a set of discrete lump masses, spring and dashpot, and in that approach geometrical damping is difficult to account, however nonlinearity can be considered. So ultimately you can observe that whatever the advantage of the first case is the limitation of the second approach, and what was the limitation of the first approach is the advantage in the second one. So first and second approach both have some drawbacks. So there is a third approach, which is typically, you may be aware about that in engineering if you do not find any solution, then finite element is a so nice method that using finite element you can find the solution for any problem, though it comes at a high cost of computation. So the finite element analysis overcomes the limitation of the above the both approaches, where you can consider the geometrical damping as well as nonlinearity of the soil. However, computation cost increases And the second thing, you may be aware that finite element solutions are not exact one, they are approximate, and how approximate, it depends on many factors, for example size of the elements and time step and all these things are there. So, these are the 3 approaches. So, continue with that. So, what we are going to discuss, particularly when we talk about lateral load and as well as vertical vibrations, we are going to focus on the second approach, because it will be difficult to cover at this stage the finite element approach. Finite element approach, we just can talk about that you can model 3-dimensional modeling or 2-dimensional modeling, and then you can do. So, our focus will be on the second approach, which is that is discrete models. So, using that, now we are going to talk about piles under vertical vibration. When we talk about piles under vertical vibrations, there are many researchers earlier. Earliest one is Barkan in 1962, and you may be aware that Barkan worked a lot on machine foundations, and he proposed determination of soil pile stiffness from cyclic vertical pile load test similar to a cyclic plate load test, which has been published in Prakash and Puri in 1988. Here one thing you need to be understand that when we talk about for dynamic analysis of pile is not a single, rather it is a soil pile system. So, whenever we talk about the stiffness, and then it will be better to have the soil pile stiffness, and so what has been proposed, that determine the stiffness of soil pile system using some cyclic plate load test, and then plot a load P and elastic settlement Z1, which may be represented by a straight line up to the working load in many situations. So, the relation between force and displacement could be elastic up to certain limit, and if we assume that elastic conditions prevail or let us say neglecting the nullity of the soil, then the constant of proportionality K, the coefficient of elastic resistance of pile, can be work out P divided by Z1, where Z1 is elastic deflection of pile and P is the force applied for the Z1. If you increase the value of P, you will increase the value of Z1 also. However, as you may be aware that the soil is not a linear one, rather the property of the soil is non-linear, and particularly at strong ground motion or whenever you apply high excitation. So, it represents the load required to induce a unit elastic settlement of the pile. The coefficient of elastic resistance of the pile depends on soil properties, pile characteristics, which are for example length, and the length of the time the pile has been in the soil. For example, the elastic resistance of pile may have different values during driving and sometime later, particularly in soft clays. So, the natural frequency of the pile in the vertical vibration is then given by f and z 1 by 2 pi root k by m. So, this is the case there. Now, what you have? The natural frequency is given by this case, the second equation, and then the second equation is simple, like omega n equal to k by m, where k is the stiffness, which we have talked, and mass is the. So, this is the natural equation, which is for single degree of freedom system, you may be aware. And based on the above simple concept, what has been done by Barkan in 1962, the transcribed test data and typical values for the natural frequencies for different cases of elastic constant of piles and pile group under both vertical and horizontal vibrations. However, this analysis does not consider the damping in the system and the dynamics of the problem. Further, the soil modulus depends upon the strain in the soil. So, K was assumed elastic. However, the value of K in equation 2 will have different for machine foundation problems and for earthquake loading. Actually, the K is what is called strain dependent, which we are going to talk about that, and there is no simple and direct relationship between strain in the soil along a pile, particularly in horizontal vibration, and soil deformation around the piles are available. So, the issue is this one, in equation 2 the K has been assumed elastic. However, this is not the case. If this is not the case and K varies with the strain, so basically this is elastic soil constant E, Young's modulus, G shear modulus, and K are strain or displacement dependent. So, which is like, for example, you may be aware in equivalent linear model, shear modulus varies with strain and value of G by G max decreases with the strain. The values of the elastic constant K determined from a lateral deflection of the order of 3.4 mm in Barkan's test are not applicable to machine foundation problem. So, the issue is here those things for earthquake condition it is different level of strain, when you have this for machine foundation it is different. So, depending upon the level of strain we need to use the test to determine the value of K. Now, for vertical vibrations what has been done by Prakash and Puri, that they have done analysis separately for end bearing piles, and the second case is for friction piles. So, end bearing piles are those piles where you have point bearing action, or the pile tip is socketed inside the soil, rock or soil. So, that is the case. If piles are driven in soft soil or embedded in sound rock or hard sediment, their tip, the piles may be considered as end bearing piles. So, even it is not necessary that the whole of the pile is passing through the good soil condition and other things. If the condition at the pile tip is good, or the pile tip is situated in the hard rock, then this will be socketing, and it can be treated as end bearing piles. Deformation of the pile tip will not occur when dynamic loads are transferred to the pile. The pile may be considered an elastic rod fixed at its top tip and free at the top with a mass m resting on the top. So, like in this figure what has been done? In this figure the pile, though it is vertical, but now this has been like this. So, when you have this is representing, this one end is representing pile tip, the fixed end is representing pile tip, while the free end is representing pile head, and the mass m, total mass m is concentrated at the pile head. So, this is and this is amounting to your single degree of freedom system. L is the length of the pile, m is the mass. So, with this very much idealization, which is a very ideal case. So, what is this natural frequency? For this case, if no mass rests on top, then we have a solid representative column with the fixed free conditions, and resonant frequency can be found out by the relation given in equation third, omega n 2 n minus 1 pi V r divided by 2 L. What is n? N is the mode in which you want to find the natural frequency. Suppose you want to find the first mode or fundamental mode of vibration, then n should be put as 1. While V r is the velocity of longitudinal wave propagation in the rod, and the V r is here, which is given in equation 4 also. So, V r is basically here you have V r value can be find out root E by rho, and as you may be aware E is Young's modulus, while rho is mass density. So, for n equal to 1, equation third can be simplified as omega n pi V r 2 L, and as you may be aware that F1 is nothing but F1 is omega n divided by 2 pi. So, if you work out on this and once you put, then you get equation number 4. Again in equation 4 the value of V r is written as E by rho, where F1 is the natural frequency of the rod in cycles per second, Young's modulus, and rho is mass density, and L is length of pile material, which we have already discussed. Continue with this. Now, this was regarding the natural frequency or angular frequency of the piles system, pile. How about the response? Displacement u is a function of x. What is x here? X, you see that along the depth or along the height of the pile, while time t is also, so displacement u is a function of x and t, and this of a vibrating rod is given by equation number 5, where small u equal to capital U multiplied by some a cos omega n t plus b sin omega n t, where a and b are constant that depends on initial conditions or boundary conditions. U is the amplitude of displacement. So, here because u, small u is a function of, it is said that u is a function of x and t, while this is function of t only, that means capital U need to be a function of x, and that has been given in equation number 6. So, where and with this condition a function, that means it is assumed that along the depth of the pile the displacement amplitude varies is with a sine function of omega n x divided by V r. So, omega n has been already defined, and d is again some constant which will represent basically an amplitude, not dimensionless. So, what you have here that capital U is a function of x while you have another t. So, that means small u is a function of x and t. What is capital U here? Is a function of x which defines displacement. Omega n natural frequency of road, which we have already discussed, and omega n is given by the relation third. Then you have ABD constant and t is time. So, using the equation number 5 and 6, you can find the displacement at any time t at any depth x. Then what has been done to get this solution of this, to applying this boundary condition to find the value of a, b and d constants, we do some manipulation, some simplification. So, what is done? First is the derivatives of the u with respect to x, which will basically represent the slope, can be given by equation number 7a, while the second derivative of small u with respect to time is given by 7b. Now, what you have, the force displacement relationship is given by equation number 8, where F is del u by del x into AE. And what we do in this equation, we put u, delta u is instead of u, you can put this should be equal to this on the force should be equal to mass multiplied by acceleration, and because this inertial force will resist the motion. So, negative sign has been used in equation number 8, and in equation number 8 del u by del x and del square u or del t square is put from equation 7a and 7b. Using equation 7a and 7b, equation 8 can be written as given by equation 9. So, now in this equation 9 represent this equilibrium of the inertial force and this resisting force on one side. So, what you have here, when you simplify this further, equation 9, then the equation 9 can be written in the form which is given equation number 10a, which is further simplified in 10b. So, 10b is the finally outcome of the equation, which is a relation between you have this weight of this a is again constant. So, finally, in equation 10th b you have only one constant, that is the a, and which is basically representing your amplitude for displacement, and this a and b will have the same unit as a unit of u. So, in fact, a, b and d they are not dimensionless, they will have same unit as a displacements. And so, using this relation, because L is known, gamma is known, W is known, VR can be known if you know the soil property. So, using equation 10b you can find the value of A, or you can directly plot equation 10b as shown in the next figure. Here you need to understand that in this equation both sides are you have this side AL into gamma divided by W, and then on another side. So, they have the same dimensions of both the sides, and this can be plotted as given in figure 10. So, in the figure 10 what you have AL gamma over W, and where W is weight of the added mass. So, if you have A into AL, A is again displacement, and so this is if you consider it then this will be actually this y x axis you have the AL into gamma into divided by W, while on y axis you have this the frequency ratio, that is 2 pi Fn, which is 2 pi Fn is nothing but basically omega n. So, because omega n divided by 2 pi will be Fn. So, that's you have into L divided by Vr, which will be dimensionless. So, here you could see from this plot that x axis is first of all on the log scale, while y axis on this plot is not on the log scale. But then if I see here that this is ultimately ending up, this end will be when it is 2 pi by 2. When you have this 2 pi by 2, then it will be this factor AL gamma or W will be going to infinity if this is the case there. So, this is the variation there, and not only that, for the in this plot for the natural frequency, which is find out from the equation earlier equation, equation number 4 and equation 3rd and 4th. So, fourth equation gives you the natural frequency that has been also plotted for different length of the pile in this this graph. So, you could see here the problem is given here, W is the weight, total weight on the top of the pile, L is the length, and you have additional stress this W by A, which is due to the exclusively this W by A is due to the weight. And then you have for different pile lengths you get the natural frequency in cycles per minute. Here you could see that both x axis as well as y axis are on the log scale, and then you have a number of curves here depending on the different material, steel, concrete, and then you have wood. So, with that you can find out the natural frequency of the system given the pile length and other parameters. So, select the pile length, also select your material and what is this sigma A axis actual stress, and accordingly you can find the value of natural frequency from this chart also directly. So, this was the case for end bearing piles. Prakash and Puri continue for friction piles or floating piles. In floating piles, unlike end bearing piles, the load is transferred from the shaft to the soil. Okay. So, basically it is not the end bearing action, rather load is transferred towards the soil itself, and their analysis under vertical vibration is quite different than that for end bearing piles. Some of the methods employed to determine the response of floating piles to vertical dynamic loads are as follows. So, which these are the similar to what we have discussed, 3-dimensional analysis, and that can be done only using finite element method considering the propagation of waves through the pile and soil. Then solution of the one-dimensional wave equation, for example, in a manner similar to the solution of this equation to analyze the pile driving process. Then third one, an analysis of the response of lumped mass spring dashboard system representing the pile and soil. An elastic analysis in which it is assumed that the elastic waves propagate only horizontally. So, these are the assumptions for friction piles under vertical vibrations. Continuing with these assumptions, what has been done, Maxwell's lumped mass spring dashboard model, which is shown you in figure A, is approximately, but figure B is the idealized model. So, in the figure B, what has been done, you have the mass. So, this mass represent the mass on the top, you have the mass here, which is lumped mass representing a static load oscillator on the top of the pile cap, and this is single degree of freedom system, which have stiffness as well as damping, and for this stiffness and damping, mass is vibrated from this force F equal to F naught sin 2 pi F t. Okay. And when this is vibrated under this, there is a spring as well as dashboard. So, single degree of freedom system is considered there, and then for the given loading the response of the system is find out. So, as for the response for this given amplitude F naught, the amplitude of the this output or response is given by equation number 11, where in equation number 11 you find the value of Z naught, which is the maximum possible displacement for the mass, F naught amplitude of the applying load, and then properties where you have K, M and C, and in this case all three, that is mass, and then you have the stiffness and damping, all three are covered under this, and the solution differs from Barkha's solution since Maxwell considered damping in the system. So, this can be like that equation 11 will give you the displacement here, okay. And continue with this. So, what has been done, then later for the computed damping ratio xi, which is shown for a particular value of C, you know that C will ultimately end up in giving you some damping ratio xi, and for this damping ratio what you do, you find for single piles was the order of computed damping ratio was of the order of 0 to 0.04. A signifier was that for both the stiffness and the damping ratio varied with frequency. So, when they did the analysis for friction piles, what has been observed that both stiffness and damping are not constant, rather they are changed with the frequency. In particular, the response at resonance was not reliably predicted from data on stiffness damping compared to non-resonant frequency. The variation of stiffness expressed in terms of stiffness ratio K by Kn where Kn is stiffness at resonant frequency and Xi is damping ratio with frequency ratio f by Fn for the plotted in figure when f and Fn are operating at natural frequencies respectively. So, what you could see under this vertical vibration after carrying out the analysis, these are the results by this researcher Prakash and Puri. So, in the first case stiffness ratio is shown K by Kn and frequency ratio f by Fn. So, f is the operating frequency while Fn is the natural frequency and Kn is the value of K at natural frequency or resonant frequency. So, you have this ratio K by Kn and then on which is varying from 0 to 2 while frequency ratio is 0 to 3 here. So, when frequency ratio of f by Fn equal to 1, then you could see that this would be as expected 1. So, when you have this ratio 1, then naturally K by Kn should be also 1, which is shown here in the data and the base fit curve has been used. Then continue with this. As far as frequency ratio is concerned, again frequency ratio is varying from 0 to 3 while damping ratio in absolute terms is varying from 0 to 0.25, that means it could be at the most 25% damping. And for this case the legends are shown here. So, what is you could see the value of K by Kn is decreasing with the frequency while the damping ratio is increasing with the frequency. So, it was almost 0 here and then continuously exponentially increase here. So, when the frequency ratio becomes about 2 or let us say about 2.4, then you get around 25% or 24% damping ratio. So, this was the case all for vertical vibrations, and in vertical vibration we have considered two cases. One was for point bearing piles and another was for end bearing piles. Now, we are going to talk about piles under lateral loads, and let us first talk about soil pile system. Then we are going to talk about natural frequency of the system, and when we say system, it is not only the pile, it is basically soil pile system. Then we are going to talk about method of seismic analysis and design of piles, and finally we are going to discuss one numerical example also. So, let us first talk about the soil pile system which need to be considered. A reasonably practical solution for soil pile interaction under dynamic loads has been proposed by Chandrasekharan in 1974, and that has been later published as a Prakash and Chandrasekharan in 1980, and this analysis is based on the following assumptions. What are the assumptions? The pile is divided into a convenient number of segments and mass of each segment is concentrated at its center. So, let me show you this slide. What is the meaning of the first is there. You have this pile. So, try to understand that pile is passing through the soil, it is not free. So, what we do, and the properties of the soil keep varying, it is not constant with the depth. So, what is done according to wherever the soil properties are changing, then we divide the piles into a number of segments and layers of different thickness. However, for simplification in this case, it is assumed that the pile is divided into a number of segments and the length of each segment is uniform, which is delta x as shown in this figure. So, delta x and naturally the last one, the last may be different. This value may not be necessarily delta x, this could be whatever value you may have, it could be so accordingly you can have discretize, and the same thing may be on the top but here it is considered delta x. So, now what the second assumption, the soil is considered as a linear Winkler's spring and the soil reaction is separated into discrete parts at the center of the masses. The soil modulus variation is considered both linearly varying with depth and constant with depth. As we discussed earlier, that two types of variations are possible, one is constant with the depth, another is linearly varying with the depth. A fraction of the mass of the superstructure is concentrated at the pile top as empty, and empty is the mass applied on the top. The system considered is one dimensional. The pile end conditions are either completely free to undergo translation and rotation or completely rational against rotation, but free to undergo translation. Partial fixation at the pile top can be solved by interpolation. So, what has been done? Solution which we are going to consider, two conditions are considered. One condition where pile top is completely free, that means it may go rotation as well as translation. In second case, pile top is restrained against rotation, but still it may undergo translation. That means, in both the cases we are allowing the translation motion, but in one case, in the first case rotation is free, in the second case rotation is restrained. So, these we will discuss both the cases, pile top is free and pile top is restrained against rotation. So, this is the discretization which we have already discussed, that you have this delta x, delta x, delta x and this one. What has been done here, this talk about the layer second, layer third, layer 4 and so on. So, you could see that if this is the layer 2 is here to here and thickness of this layer is, for idealization, is assumed delta x. So, the delta x is here from for this layer, and half part of this will go on the top and the half part will go. So, here you have half part will go in the top and half part will be in the next bottom slide. And this when you consider the soil modulus is constant with the depth, then first idealization, then that means with the line diagram where you have the masses m2, m3, m4, mn minus 1 mn, and on the top of it you have mt. And then once you have this soil considering the soil modulus constant with depth, then you can make this model which is shown in this figure. And what you consider here, the supports are here R1, R2, R3, R4, and then you have, and with these supports you applied here, that means this support is one side, but this is representing basically the whole and you could see further modeling. So, what is done here, that the soil is replaced by the springs, and you could see that the soils are replaced by the spring here, in this case half kx delta x, kx delta x and kx delta x, and finally. So, why here, that means this is also delta x. So, all the layers are of equal length here, which is the ideal case. Then the top spring and bottom springs are only have the half kx and delta x, while the in between, if you have here, for this case what actually this node will get the contribution from the top as well as from the bottom. So, you got this, so this node will get half part from this one and half, so it will be kx into delta x throughout. So, only the top layer, top spring and bottom springs have the half, while other springs have the constant value. So, this was the case when you assume the soil modulus is constant with the depth, and the case when soil modulus is varying with the depth, we are going to talk in the next lecture, and then I will also give you the reference for this lecture as well as the next. So, this next lecture will be in continuation of this lecture, and we will talk about the case when the soil modulus is varying with the depth, and we will continue with this. Thank you very much for your kind attention. Thank you.